Good afternoon. I had a couple requests from people in Calculus Prep to do a little bit more with optimization rather than just the video going over the problems there. And since this wasn't a topic that squeezed into our curriculum this year very nicely, it was part of our plan for Calculus Prep Term 4, best laid plans, I wanted to honor those requests with just kind of a short little mini lesson talking about the process. In a sense, optimization boils down to a little bit of algebra, a little bit of differentiation and derivative analysis, and just maybe even a little bit of vocabulary just to kind of get a feel and a flavor to describe what's actually happening. In truth, though, these problems are problems that you can solve many different ways, but ideally with calculus. So my plan here, just so you know ahead of time, is I'm going to move pretty quickly, but I'm going to work through kind of an illustrative example. I'll talk about a general strategy we'll take through them, and then I'll work through 3 short examples that I think align fairly nicely with the problems on your optimization primer that you received in the Calc Prep course. So in here, I'm kicking things off by looking at this first problem, which gives us some information and requests something kind of interesting. It doesn't sound very calculus-y, really. It says the product of two numbers is 100. Find the smallest possible positive sum. So having said that, like I said, this doesn't sound very calculus-y, and in particular, as soon as you read that line stating about the product of two numbers being 100, in a sense, you might actually get a feel like you can kind of figure this out on your own. You might be able to have some good intuition here. For instance, I can write two numbers that have a product of 100, because 1 and 100 gives me 100, so that's a valid set of two numbers, 1 and 100 I mean. From there, we want the smallest positive sum, so I know that the sum here would be 101, because we just add those two numbers together. But then I start to think and go, oh, wait a second, what if I do 5 and 20? Like, that's going to be pretty nice, because that's equal to 100, but if I sum those two numbers, I get a sum of only 25, and that's pretty good as well. But then the question becomes, what about 4 and 25? Like, well, that's a little bit bigger, but at the same time, you can kind of see there's not really this intuition about where to go. Now, having said that, you might be able to say that obviously the answer is going to be something that's closer to a perfect square, and your intuition would be correct if that was true. You've probably run into problems like this before without having any calculus behind you. And that's fine. Obviously, if you can answer the question without calculus, that's wonderful, but our goal here is to use calculus to illustrate this and attack this problem, this type of problem called an optimization problem. So what we're going to do instead is we're going to try to set this up and come up with almost a system, like a system that's going to be solvable via differentiation as well as substitution. Not substitution like chain rule necessarily, just substitution. So what we're going to do is I'm going to begin with this thing that I underlined in pink. It says the product of two numbers is 100. That in itself restricts us as far as numbers we can choose. So for instance, this would not be a situation where I could choose the two numbers to be 42 and 42. The reason why is, of course, their product is not 100. We're told, we're kind of limited in our choices of numbers to having their product be equal to 100. And the reason that's valuable is that gives us kind of a huge piece of information as we go to attack this problem. It gives us what we call our constraint equation. And a constraint, if you know what it means to constrain something, is to like hold them. It's almost like constricting, like you can't let them move, like they can't go anywhere. They limit your movement. So if in this case we have a constraint equation, it's got to be something that limits our choices. And telling us the product has to be 100 is one way of constraining our choice of possible numbers. So as far as numbers, I'm going to call them x and y. And since we're talking about the product being 100, I'm going to say x times y is equal to 100. And there is our first bit of work. We now have a constraint equation. Notice that that equation has two variables for only one equation, so two unknowns, so we can't necessarily solve it by itself, but that's okay, because our goal is not quite solving for x or y just yet. Now the second piece of information in here, though, is something that otherwise might seem like it's not going to be solvable here. I mean, we can guess it, but you get the idea. It says we want the smallest possible positive sum. So what we're trying to get here, this is kind of our goal. Like the purpose of this work is to find the smallest sum, which is another way of saying that we want the minimum sum, which is honestly a really fun thing to say. The minimum sum. Sounds very British then. So we want the minimum sum. So what that creates is our second equation, which again, this name isn't the important part, but it fits nicely. If our goal is to find a minimum, it's our objective as well. Goal and objective mean the same thing in this case. It's our purpose in this problem. So in this case, our objective is to get a minimum for the sum. And if we want to talk about the sum of those two numbers, since we called them x and y, their sum would just be x plus y. And so we now have a second equation. The only difference is this green equation is what we want to find the best value for, in this case the smallest value for. So we're going to try to find the smallest possible sum of this guy. But once again we run into that issue. We have 3 variables in one equation, we have 2 variables in the other. Your mind goes, this is completely unsolvable, blow it all up, it's not going anywhere. But that's not the case. Instead, let me point out that in addition to being frustrated by the fact that the minute I started recording this video, someone began leaf blowing their lawn, probably just blowing the leaves onto my lawn, by the way. Thanks for that. Setting all that aside, instead let me point out that what we can do is we can actually substitute from one equation to the other. So I'm going to focus my attention right here. If x times y is equal to 100, then would you not agree that y is equal to 100 over x as well? Those are equivalent equations. In fact, it's tempting to put it in pink just because they mean the same thing. But given that, what we can do is now that we've solved for one variable in terms of the other, we can go ahead and substitute it into the objective equation. And that will give us instead that s is equal to x plus 100 divided by x. And this equation still does have 2 unknowns, I can't deny that. But remember, we're trying to find the maximum value of this one, so in a sense it's no different than me asking you what is the maximum of this equation. The only difference is we can't call it y, because y means something else. So instead we just call it s, and we're going to find a maximum. Now finding a maximum would be easy if we just graphed it on the calculator, but again I'm presenting the possibility that this doesn't need to be done in the calculator. So instead what we want to do is we want to think about how do we get a maximum, or in this case I keep saying maximum, I mean minimum. How do we get a minimum from an equation? Well, what we've normally done is we've taken its derivative and set that derivative equal to 0. So that's exactly what we're going to do right here. So we're going to take the derivative of this equation and set it equal to 0. So that's pretty simple. If we take the derivative of s, we're going to get 1 and then minus 100 over x squared. And then that's our derivative, so we want to set it equal to 0. So good enough. By the way, we do have to be a little more careful here. Technically, there are some issues, like x is equals 0 is not in the domain, but we're going to set that aside. For the moment, instead, we'll just keep solving. So if I move something to the other side, I'll get that 1 is equal to 100 over x squared. That's going to tell us that x squared is equal to 100. And that's going to tell us that x is equal to either negative 10 or positive 10. But remember, we want a positive sum, and a positive sum is not going to come from having a negative number. So instead, we're just going to focus on the likelihood that x equals 10 is going to be our first number. So I'm going to make that my assumption. We'll verify it in just a little bit. So if x equals 10 is our critical number, and that's really what we just found was a critical number, a critical value. If x equals 10, then we can go back to our original equation, which was in pink, recall, or even in this burnt red, either of those possibilities. We can pull that down and say that then, well, y is going to equal 100 divided by 10 as well, which is equal to 10. So that gives us our potential solution. We can now conclude that x is equal to 10 and y is equal to 10. So if those two numbers have the same value, then their sum is minimized. So makes enough sense, like that's simple enough. But then the question might be, is that enough? Have we proven it all? Like, have we done everything that we possibly can? And there are some options here. Technically, if we wanted to do this as formally as possible, we'd want to use the candidates test. But it's a little hard because, like, the product of two numbers, there's lots of possible numbers out there. So instead, let me just point out that we can at least make sure that this value we found, x equals 10, corresponds to a minimum. And now this isn't a part of the actual assignment that you're doing, but I do want to illustrate it at least one time just to make sure that you've got it. But if you need to justify your answer, it would be helpful to know if it's actually a minimum. So what I'm going to use is I'm going to use the second derivative test. Oops, I'm going to miswrite it, and then I'm going to use the second derivative test. So the second derivative test, recall, requires you to check that the value is a critical number, meaning that it makes the derivative 0 or undefined. And then second, checking the sign of the second derivative. So in here, if we use the second derivative test, we have that s prime of 10 is equal to 0, because that was basically all the solving work we did right there. And then in addition to that, we next want to talk about s double prime of x. If we take the derivative of s prime, that's going to be, it looks like 200 over x cubed. And if we evaluate that at x equals 10, we're going to get something that is clearly positive. And basically you're putting in 200 over 1,000, which is 1/5, which is definitely positive. So what we've just shown is that s prime of 10 equals 0, and s double prime of 10 is greater than 0, which implies s is concave up. I'm going to abbreviate here, I apologize, at x equals 10, which implies that we did in fact find a minimum. So now, having said that, we've finished this problem. There is one small issue here that you might have already noticed, and you might already be posting in a comment to say, wait, you did it wrong, and you'd be correct. The problem here is that I boxed my answer as x equals 10 and y equals 10, but that wasn't what the question asked us for. It asked us for the smallest positive sum. So unfortunately, if we want to do this correctly, we need to actually find the smallest sum. So from there, our actual smallest sum, which I'm going to call s sub min, is going to equal 10 plus 10, which equals 20. And there is our smallest possible sum. We found it using calculus. Yes, you could have found this without calculus, but that won't be the case in every single problem. So there is kind of an outline of your minimization strategy, or your optimization strategy. Now, if you want to kind of line that up and just kind of think about what we did, just kind of step by step, and see a general strategy for approaching this, the first place where I begin is I talk about the constraint and the objective equations. Basically, I first try to figure out what's limiting us to get an equation that just has 2 variables. And then second, I want to come up with my objective function, which is probably going to have 3 variables, but which is going to be what we're aiming to find the maximum or minimum value for. And when we say optimize, we're really just saying maximize or minimize. It just depends on the context and the question's goal. Second, it says to substitute from the constraint into the objective function. So if we look back on here, that's literally what we did. We worked on the left side, the pink side first. We solved for 1 variable, and then we substituted that into the green side to come up with our equation. That was in 2 variables, yes, but it was all an explicit function of 1 variable. After that, we can differentiate and set the derivative equal to 0. Fairly standard, although again, domain restrictions may apply, so keep an eye on those things. And then finally, step 4, which is not the focal point of the work we're doing in Calc Prep. We just wanted you to get comfortable with the computation, but you would be responsible for normally interpreting your answer. So in other words, answering the question correctly, not just putting down whatever your critical numbers were, and justifying your answer. And that justification can be the first derivative test. So checking if f prime changes positive to negative or negative to positive. It could also be the second derivative test. And I should have written this ahead of time, I apologize. And then third, although it hasn't necessarily come up on the problems that we include in here, it could also be the candidates test. It just depends on the context of what's there. As I said, I'm pretty sure almost all of these have been, like the candidates test part has been neutered, but the idea is there. So there is kind of our general strategy for approaching an optimization problem, but you'll get a feel that it's an optimization context because you've got kind of 2 different things or 2 different equations kind of starting, and your job is to bridge them together into one beautiful equation, take its derivative, set it equal to 0, and then find the maximum or minimum. So let's look at a couple of little examples. So the next one we're going to look at resembles that first one just a little bit. I'm going to move through it pretty quickly because I don't think this is as essential as the others. It says the sum of a number and twice another number is 100. And by the way, when they start talking about things like a number and another number, as a heads up, you're probably just going to want to call them x and y. That usually works fairly well, and I don't want you to waste time trying to decide should they be Steve and Terry or should they be Joe and Carol. It's a fairly recent allusion. After that, it says find the largest possible product of these 2 numbers. So now I'm going to use the same color scheme I did on the first one. So words that indicate that you're looking at the objective function, it says find the largest possible product of these 2 numbers. So that's a huge starting spot, but specifically the word largest. When you're asked to find the biggest something, that tells you automatically that you're looking at your objective function. And because it's largest, that tells me we're looking for a max. So in here, we want the largest possible product of 2 numbers. And I know that products can call p. And since I said I want to call my 2 numbers x and y, I'm going to let p equal x times y. That's what we're going to be optimizing. We want to find the biggest value that can attain given the other information. Now second, they start telling us some information about the sum of the number and the twice another number. So they're giving us some information here, which is a little bit awkward, but that is obviously going to be our constraint. So our constraint is what we're stuck with. We can't just choose, if we want to find the largest possible product, we can't choose 10 trillion and 26 billion 42, because then the sum of one number and twice the other won't be 100. So we're limited by what we can choose. We are constrained by that first statement. So now there's lots of different ways you could write this. They'll all lead to the same answer, just in different pathways. But I want to write this as 2x plus y equals 100. And again, I have a little bit of foresight here, although I actually haven't done this problem before. I recreated it, or created it this morning with no practice. So here is our constraint, here's our objective. What are we going to do? Same thing we did before. We're going to take our constraint equation and solve for one variable in terms of the other. And in fact, I'm realizing that I should have just taken this with me and brought it to our side. Brought it to the dark side. Just throw that over there so it's around. There's our old friend, the plan. Okay, so our equation 2x plus y equals 100. Once again, I'm going to choose to solve for y. I think that's going to be a choose for y's thing to do. Then from here, if we want to solve this all in or we want to be able to attack this objective function, we need to get it in terms of just one variable. So I'm going to choose to get it in terms of x. It's going to be x times y, and my y equation is going to be this guy. So we're going to have 100 minus 2x. Naturally, if we multiply this out by distributing, we'll get 100x minus 2x squared. So that is our objective function, our product in terms of x and y. We want to go ahead and find where this is going to have its largest value. So we can do that by taking the derivative of p and setting it equal to 0. So in this case, it's going to be pretty clean. The derivative is 100 minus 4x. Oh, cool, this works out nicely. If we set that equal to 0, it's pretty trivial to see that x is equal to 25. So this is giving us a good idea that we've found a potential maximum or minimum. So from here, if x is equal to 25, then we can go back into our equation. We'll get that y is equal to 100 minus 2 times 25. And that y value that's going to come out is going to be 50. So what we've just found is that in this maximum situation, at least apparently, we'll get that x is 25 and y is equal to 50. So those look like our answer. It's easy to say that's our answer, but keep in mind, we're supposed to find the product of those two numbers. So if we want to find what we're going to call P max, the maximum or largest product, I would expect that to be 25 times 50. And geez, let me see, I think I can do this. This is the same thing, but this is unnecessary arithmetic. I just get a kick out of it. That's the same thing as 2,500 over 2, which is 1250. So the largest possible product is apparently 1250. Now, if you wanted to do that last step and verify it, this one's particularly easy. P double prime of x, at least easy when using the second derivative test. P double prime of x is equal to -4, literally because P prime is a line. -4 is less than 0, which tells us that P is concave down at x equals 25, which of course indicates, therefore, that we have a relative maximum. Voila, there we go. So there is our work. Again, very similar problem to the first one, but you can see that that pace works really nicely, moves pretty quickly. So very kind of sterile version of the problem. Let's look at the last two ones here that are a little bit more authentic, we'll call them. So in problem number 1 here, it's not really number 1. For us, it's number 3, I think. I think it's 3. So in this question, it says Farmer Bob wants to raise goats and velociraptors, as one does. But he needs to keep them separated for obvious reasons. Yes, he's watched the Jurassic Park series. 2 franchises? I don't know, double franchise. Farmer Bob decides to erect a rectangular pen with 2 separate partitioned regions, but he only has 300 linear feet of electrified titanium human fencing. Oh my! Could buy more. I guess you could eBay it, or I've heard Lowe's parking lots are busy. Maybe people are doing some home improvement. It says find the largest area that he can enclose with this much fencing and the dimensions of the corresponding pen. So again, in this case, just as a heads up, I am going to choose not to interpret and justify. I'm doing it to save time, that's it, but I'm going to do the rest of the problem. So in here, it's a little bit about reading. We're trying to navigate this problem and find both the constraint and the objective functions. So let's see if we can begin with something that constrains him. And I think this one's pretty clear. He only has 300 feet of fencing. So setting aside the fact that maybe the electrified titanium fencing isn't appropriate for a humble farmer, who knows? I guess he's farming velociraptors, which are extinct, but whatever. Basically, we've only got 300 feet of fencing. So it's easy for us to begin this constraint by saying 300 equals, but then that's where we run into our issue. Like, what does this pen actually look like? There's a lot more going on here. So what else do we know? We have a rectangular pen. It has two separate partitioned regions. So there's a lot of verbiage in there, but when you partition something, it's just you divide it into two parts. So what we're talking about with Farmer Bob is he's got this little rectangle here. Looks great. And he's going to have two separate partitioned regions. So basically that means he has to have another bit of fencing to separate those sections. Otherwise the goats are going to have a bad time. So he needs that much. That's our setup. So in here I want to go ahead and call these two different variables. I'm going to call this W and I'm going to call this L. But because of the way I do this, and assuming that Farmer Bob wants to be generous to both his goats and raptors and give each of them a chance to live, I need to also call this L. And the reason I'm writing all this stuff out so explicitly is because I need to turn this into a model. Because really, if we're trying to say that he only has 300 feet of fencing, that means that the sum of all these variables is constrained to be 300 feet long. That's all he has available, so that's all he's got to go with. So looking in here, I notice that we have 3 W's, and I notice that we have 4 L's. So basically, given that information, we now have our constraint equation. In a sense, the constraint in this situation was basically the perimeter. And perimeter might not be the perfect word because that intermediate fence maybe doesn't fit the definition of perimeter, but it's pretty good. For our second one, we're talking about the objective, and this is pretty easy. It says largest area. When you see the largest or smallest or maximum or minimum, that is your clue that you're looking at the objective function. So we want area. Now it's natural for people to write area and just go length times width, blah. But look at our picture. Length times width is not the area of that particular rectangular drawing. Instead, because we have 2 L's on the side, our area is actually 2L times W. So we do have to be a little bit careful. So one of those things to watch out for sure. So given that we now have that, our objective function was our area, and we are trying to maximize it, because of course Farmer Bob wants his goats and raptors to be the healthiest of all goats and raptors. And actually by producing raptors, they will by definition be the healthiest because they are extinct. But setting that aside, we can attack the problem now that we have it. So this one's not going to be quite as clean as it has been in other cases, but we need to solve for one variable, and I'm going to go ahead and take the L over to the other side. Yes, that was a funny line. I just can't reach for the other one because I'm trying to save time. So in here we have 300 minus 4L equals 3W. I'm going to go ahead and divide both sides by 3. We'll get that W is equal to 100 minus 4/3 L. Now you might look at this and go, oh, there's no way I was going to solve for L. And that's fine. Be you. Like, it doesn't matter to me. Like, you can do the same thing. We'll get to the same place at the end. We'll get the same dimensions and we'll get the same area, maximum area. We'll just get there through different paths. And I don't really care how you get there as long as it's mathematically sound. So now that we have that set up, our area equation is going to end up being in function of L. We have 2L times W, and our W is this 100 minus 4/3 L. So there is our equation. We'll go ahead and distribute in there to clean this up. You can see these things aren't difficult algebraically. They're pretty clean, actually. 200L minus 8/3 L squared. That is going to be our area. What do we want to do from here? Well, naturally, we want to go ahead and find the maximum. So we're going to go ahead and take this. We're going to compute A prime. And it'll be A prime of L, not that we've been using that too much. A prime is going to be 200 minus, it looks like it's going to be 16/3 L. Let me make sure I did that correctly. It looks like it is correct. We're going to set that equal to 0 to find a potential maximum or minimum. When we do, we're going to get that 200, oops, sorry, I should do an implied sign here. My apologies. We get that 200 is going to equal 16/3 times L. If we want to solve this, we're going to get that, let's see if I do this right. Yeah, it's going to be 600 over 16 is equal to L. And now it's a matter of knowing what 600 over 16 is equal to, so doing some quick arithmetic, some quick maths. We're going to get 150 over 4, which is going to be 75 over 2. So, is that right? Let me just make sure I did that right. Yeah, it is right. It's just annoying. Okay, so we've got our L value. So we can go back over here and proceed. We found that L has to be 75 over 2. Given that, we can calculate our W value. W is going to be 100 minus 4/3 of our value for L, which was 75 over 2. When we multiply this through, clean it up a little bit, we'll get 25. It's going to be 2 over 1. So interestingly enough, our width is going to be equal to 50. I haven't been using units, I apologize, but I guess some of the units haven't popped up yet. So we got 50. So it turns out we've got both our answers here. We have that the length, or the value of L, let's be careful, the value of L needs to be 75 over 2. The width has to be 50. I think that's given us what we need. So in here, though, if we're going to calculate this all out, we got a couple things to answer. So we were asked for the largest area. So what I'm going to call A max is going to be equal to 2L times W, but evaluated at 75 over 2 and 50. So in here, what that's going to give me is 2 times 75 over 2, and then times 50 as well. Obviously, the 2's go away. We get 75 times 50. That's 7,500. Cut it in half is 3,750. And if we want to go ahead and put that in units, since it's an area, it would be 3,750 feet squared. So that is our maximum area. As far as the dimensions of the pen, there's lots of different ways you could do this. You could report the values of L and W to match your picture. But if you wanted to just talk about the total pen, like the entire pen, I'll call this, the entire pen that they'd be housing these creatures in, the entire pen would be 75 feet by 50 feet. And that way I've got like the best, most descriptive way. Describing the outside is fine. So this will create the maximum area, and it'll create the maximum area, I believe, for both or each of those two creatures. So again, there's a little bit of modeling you had to do. You had to draw that picture geometrically, and there's a little bit interesting algebra, or at least number-wise. It came out a little bit crunchier than the previous ones, but it works out just fine. The final problem we're going to hit is one that oftentimes, truthfully, when I used to give this in the past, people just punch in their calculator and be like, this isn't that hard. But again, we're presenting the possibility that you won't have a calculator handy. So I want to present this instead as I would normally. So in here, there's going to be some issues, but we'll play along. So in here, we're asked to find the point on the parabola, y equals 9 minus x squared, that is closest to the point 3, 9. So in here, if we want to picture this situation and visualize, and visualization is a powerful thing. I don't know if I said visualization correctly there, but the idea is good. We've got this 9 minus x squared parabola. Oh, what a glorious parabola. This point, by the way, right up here, is going to be the point 0, 9 on the parabola. And these will be -3 and 3 respectively. Now what we're curious about, though, is the point. Like, where on the parabola are we going to be closest to the point? Literally right here. The point 3, 9. We want to minimize this distance. Now, if I had Desmos queued up already, I'd go ahead and show you. I have this cool little demo that actually shows the different lengths that are in there. But for the moment, like, you can probably just visualize it from my lovely picture here. We're trying to find the shortest one of these lengths. And honestly, you can probably see where that shortest length is. It's right here. And if you've already looked at some of the video for the problem set that we posted, you'll actually know that there's a way that you can do this using a combination of calculus and just basic linear algebra. That is, the point that's going to be closest will be the one at which the tangent line and normal line are perpendicular. So, or the normal line through that point is perpendicular to the tangent line. So in any event, there are ways you can get here, but our question, of course, is to actually find that, and again, use calculus as best we can. So in here, in this problem, we have a couple things. This is a little bit awkward, But at the same time, like, it's definitely good information to pull up here. First and foremost, you should know what the distance formula is. I'm going to call it little d just so that way it's a little easier. But the distance formula for the distance between 2 points would be x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So the reason that's important, or where you could get that if you're not sure, is it's literally just the Pythagorean theorem. If you've got 2 points here and you draw a right triangle out of them, you can get their change in x and the change in y. In fact, it's something you've probably done before, maybe even in this class. But setting that aside, there's our distance formula. Now, as far as constraint and objective, we're trying to maximize this equation. So I would be tempted to throw this up here. Is that what I did before? I guess I sort of did. It's tempting to put something like that up there, but I actually want to take one extra step before I do. Instead, I want to point out that our constraint is actually pretty well established for us. We've got the parabola restricting what point we choose, because although you might not think about it, we can't choose this point right here that's super close to the point we want because it's not on the parabola. So really the parabola is constraining us. And then also technically is the ordered pair itself. If we change the ordered pair, the answer would obviously change. There's going to be a unique point on the parabola that's closest to any point we choose. So those are kind of my constraint, and the reason I bring that up is that it allows us to already kind of set up our distance formula a little bit before we jump in. Specifically, we have some information here, and it's going to come from both of these two equations. Although, you know what the heck, let's just go ahead and treat it as the objective for the moment. Who cares? I actually really like doing this problem. I know this one's not going to end the way I want it to, but it's a good problem. Okay, so what do we want to do here? Other than shift that over and color it green to stay consistent with my entire thing, what I want to point out here is all about this constraint information. So if we want to talk about those two ordered pairs, x sub 1, y sub 1, and x sub 2, y sub 2, we've got to use the information from the constraint equation, not just because I wrote those things in pink. So in here, if we want to make a point, I'm going to go ahead and call x sub 1, y sub 1 the point 3, 9. The reason that's valuable is if we go into our objective function, the thing we're trying to get the shortest value for, so the minimum, and go ahead and replace those guys. I was going to say replace those puppies, but this is a time in the world when we all need puppies. So from right there, I'm going to go there. As far as our second point, this one's a little more subtle, but basically we need to be on the parabola, so we need to find something that represents any point that's on this parabola. Obviously some of these are bad candidates, but the idea is right. So what I'm going to do is I'm going to call this other point x comma y. But remember, we said that y is equal to 9 minus x squared. So instead, why don't I just call it x comma 9 minus x squared? When I do that, or by doing that, what I can do is once more, I can change the way this is written. I'm going to go ahead and write this as x minus 3 squared. And then for y, this is not going to fit quite in, but we're going to get 9 minus x squared minus 9 squared to get the y in there. And so this guy is actually going to be our equation that we try to optimize. I'm sorry you can hear my throat going. I left my water in the kitchen. I haven't eaten lunch yet, but I'm going to get this done. Then I can render it while I eat lunch and feel like my life is efficient. Okay, so in here, obviously, we want to work on this equation. So I'm going to go ahead and do a little bit of work to clean it up. So in this case, we're going to get an improved version of d. So we've got the square root, beautiful radical I just drew there. X minus 3 squared is x squared minus 6x plus 9. And on that next one, we have 9 minus x squared minus 9 squared. And I bet you notice that the 9's actually zero out, which means this radical can actually be written instead. It's going to look kind of radical. I'm sorry. But we've got x squared squared, which is going to give us a term of x to the fourth. Then we've got plus x squared minus 6x plus 9. So there is our formula. That's what we're trying to differ, or that's what we're going to be trying to optimize. And are you kidding me? Thank you, computer. Computer. Okay, so we're going to try to optimize this guy. We want the maximum value of this. And truthfully, nowadays you probably don't panic when you see it, but having said that, I could imagine people looking going, oh, this is going to be terrible, but just patience. What we're going to do is we're going to take the derivative. So I want to get what I'm going to call d prime of x. When I differentiate this radical, I'm going to, of course, have to use the chain rule. The chain rule cannot be avoided here. You are locked to it like someone's locked to chains. In our chain rule, though, we've got the derivative of the square root, which is just 1 over 2 times the square root of stuff. And then afterwards, we're going to multiply by the derivative of that stuff. So we're going to multiply by the derivative of the radicand, which isn't that bad. It's just a polynomial as such. When we do, notice I didn't write anything in there. I'm just going to put stuff in there. Why not? I'm just going to stuff it with stuff. Our derivative is going to be, it looks like, 4x cubed plus 2x minus 6. And then down below, we'll have 2 square root of complicated things that I wish I didn't have to write, but the world says so. So there is our derivative. Now we want to set this equal to 0, and we have no issue down below, by the way. There should be no issue with that being negative or being equal to 0 at any time. Instead, though, I need to set the derivative, that numerator, equal to 0. So basically, if I do that, if I solve 4x cubed plus 2x minus 6 equal to 0, then I have to find my x value. Now, I don't have a good way to solve this for you that doesn't require us to use P and Q, like all that good stuff, the rational roots test. But I do want to point out that if there was no x here or x here, 4 plus 2 minus 6 does equal 0, which tells me that one such solution is x equals 1. This is, in fact, the solution that I was looking for. So in this case, you can find and use your calculator if you want to. This problem's not perfectly suited like the one on your problem set is that Ms. Formaker wrote. But we can get our one value just by inspection. Like, you can factor it too if you happen to know ways to do that. If x equals 1, then as we've done before, we can go back to our original equation, or our constraint, and since y has to equal 9 minus x squared, we can substitute in our 1, and that will give us 9 minus 1 equals 8. So what that tells us is the point that's going to be closest on the parabola, of course, is going to be the point 1, 8. And so, interestingly enough, we have our answer, and it turned out to be pretty clean. The only problem was, of course, we did have to cheat a little algebraically. But in any event, we have gotten our answer, and we used calculus. We were using it pretty strategically. In fact, it worked really nicely. So having said that, again, as I mentioned, this isn't an ideal lesson. This isn't what I'd like to do. I'd love to give you one to try and everything, but that wasn't the goal here. The goal here was to just kind of work through some problems and give you a tool, so if you wanted a quick reference on how to approach optimization, you could absolutely do that, and I feel like I've accomplished that. So having said that, because I'm thirsty, my throat hurts, I feel sick, and I need to eat lunch, I'm going to call it a day, but hopefully this video has been helpful to you and given you a little bit more insight into the optimization process. And again, in the time when your life is far from optimized, thanks COVID, it's nice to have something optimized all the same. So whether you watched or not, have a great day.